So this is the 10th lecture video for 7600, and it's going to cover some additional material about file systems. So we'll start out by looking at the ext2 file system. That's a Linux file system. It was the primary one for a number of years early on, and it's essentially a straightforward implementation of the ideas in the Berkeley fast file system. If you're interested, you can go and look at Marshall McCusick's book about the Berkeley Unix operating system, and it'll have the exact details of the fast file system. But this is basically the same thing. So the file system is organized into, first, a superblock, which is found at the beginning of the file system. It turns out they leave the first part of it blank for historical reasons having to do with DOS boot blocks. And it contains all the parameters for the file system. So block size, it might be 1K, 2K, 4K. The version. So over time, they've added features to it, and so you can know what version. This way, a newer version of the code can interpret an older version on disk. Various feature flags. So there's a number of optional characteristics a volume can have. And you flag in the superblock whether those are enabled or not. There's a state, clean or dirty. When you mount the file system, you mark the state as dirty. When you unmount the file system after all the data is flushed back to disk, you change this flag back to clean. One last write to the superblock, and you change this to clean. So if the system crashes while the file system is dirty, you know that on reboot it has to be checked for consistency, whereas if it was shut down cleanly, you can skip that step. And then finally, and so it also has things like the size, the number of inodes and blocks, what the reserved fraction is, whether it's 90%, 95%, and so on. That's actually expressed as how many reserved blocks are there. Next, you have block group descriptors, and then finally you have a series of block groups. So I'll describe a block group because it doesn't make sense to describe the descriptors until you've seen what the group is. A block group, so what the fast file system did was, for locality, it created what they called cylinder groups. There are block groups in ext2 with the idea that you want to allocate the inodes and the data blocks for a directory and its files close to each other. So a block group has a block bitmap that's used for allocating, and this is one block. It's used for allocating blocks within this group. So the length of the group is going to be 8K blocks if we have a 1K block size. 8 times 10, 24, 16K, up through 64K if we have, 32K if we have a 4K block size. Then there's another block that's the inode bitmap. Now, you'll notice that we've already used up the first two blocks in this group, so we're going to have to flag them in the block bitmap. They're never going to be available for allocation. Similarly, there's a certain number of blocks that are going to be used as the inodes. So each block in here is going to be carved up into 128-byte inodes. And then the remainder of this is the data blocks. So if we want to, this looks like a mini file system. It's got the allocation structures for blocks and inodes, and then it's got the data blocks. And then there's a set of descriptors here, basically keeping track of all the block groups and how much free space there is in each of them, and so on. Okay, I forgot one last thing here. We have to identify the root inode. That's just going to be a number, 15 or something. Now, it turns out that each block group, and it also has the number of inodes per group and the number of blocks per group. And so, given an inode number, we just, divide it by the number of inodes per group to find out which group the inode is in, and then we can go into the table, into the inode table for that, and find, the offset within it is, obviously the number mod the number of inodes per group. And similarly, for a block, well, in fact, the block number is going to pretty much directly correspond to the block in the group. But anyway, so if we were going to create a file, finally, the last data structure is a directory. Now, like a file, a directory has an inode with a series of direct, it has the direct and indirect pointers, and so on. So we can look at the contents as just being this contiguous space, and then inside this we have variable length directory entries that have a length and then an inode number and then a name. And so we can search through this list linearly by using, at each step, the length shows us how long that entry is. We can look at that entry and then look for the next one. Now, if we delete a file, we mark its entry, I believe, with an invalid inode number. We should also check to see, if we have two deleted entries, we can coalesce them. So it turns out this starts looking very much like a memory allocator. So it's in fact a little bit of a pain to keep a directory for a file system with variable length names, but this is how it's done in, this was the approach in the fast file system. It's the approach in ext2 through ext4. Now, let's see. Okay, if we're going to create a file, we have to create a directory entry. So we have to allocate and create a directory entry. We have to allocate blocks. We have to write the data. So this is going to update the directory contents itself. So for instance, we'll search through, find some free space here, and then put our data here and our name here. It's going to quite possibly update the directory inode. In particular, we may have to extend the size of the directory file, in which case, by adding another block, in which case that gets allocated and added here. Now, allocating blocks updates the group. We have to allocate an inode. This updates the group inode bitmap. We allocate the blocks, and here we search for, actually, when we first create an empty file, we don't even have to allocate blocks. So now we can allocate, and we can create a file of length 0. That's going to update a data block containing directory contents. It's going to update the inode for the directory with at least the modification time, and possibly, if we've allocated, another block. And it's going to allocate, it's going to update the inode for the file itself. So that inode at this point will be empty, but it'll have an owner, permissions, create time, and so on. And we're going to write the inode bitmap, because we've allocated this inode, so we have to mark that it's now it's no longer free. The rules for reasonable sized directories, the rules are that we'll allocate this inode in the same block group as the directory itself. Conversely, if we were creating a subdirectory, we would pick a random block group and allocate the inode for that subdirectory in the new group. Now, if we want to write the file itself, we have to allocate a block, and for this we search the block bitmap, and we allocate n blocks, where n starts at a small number, and as long as the file is open, we keep, every time we write to it, we actually allocate an additional number of blocks, somewhere around 7 or 8, I think, is typical, consecutively. And so that way we're more likely to get contiguous allocation than if we hadn't, than if we allocated one block at a time. It's also more efficient. What that means as well is that when we close the file descriptor, we free unused pre-allocated blocks. So this is something that this is another efficiency mechanism. We're trying to ensure that we can allocate blocks that are contiguous on disk, even if multiple processes are writing to the same directory. And these blocks are going to be allocated from the current block group until the file grows beyond a certain point, at which time we'll pick another random block group to start allocating it from. So huge files will be spread across many block groups in large chunks. That way other files will also have a chance to be in the same directory. Smaller files will still get a chance to be in the same directory as their directory itself, their containing directory. Now, this actually had to change somewhat when they went to ext3, because for ext2 it was fine to actually truly allocate these and update the bitmap in memory, which would eventually be flushed to disk. If the file system wasn't unmounted cleanly, then that allocation would get undone by FSCK, because it would check and see that the file had only been written through this point, so these pre-allocated blocks could be returned. So that was the case where if you crashed, you might have the file went through here, you had this pre-allocation, because the bitmap indicated that these blocks were in use. FSCK finds that these blocks aren't owned by anyone, so it returns them. In ext3, because they added journaling, it turned out that an allocation like this couldn't get undone. So instead they use a slightly more complicated method where this pre-allocation exists only in memory. But again, you're pre-allocating some chunk of blocks when you need a new one, and then you use that chunk of blocks as without having to worry about, otherwise if you had two files being written to at once, you might find that they were allocated blocks, in an interleaved fashion like this, and that would be bad. That would give you lots of fragmentation when you tried to read one of them. Instead, each of them is going to get a nice long chunk that it can write here, and then, and the second one gets a chunk, and so on. And the rules are that this pre-allocation gets bigger as you continue to write sequentially, the moment you start writing randomly, it sets a flag saying don't pre-allocate anymore because it's not going to help this file. Okay. Allows, fast searching to find large, and because of the fact that it groups contiguous blocks together, it makes it very easy to find large contiguous spaces. Next, we'll talk about a data structure that's very important for more modern file systems, and it's been used forever for searching and indexing on disk-based files, and that's the B tree and the B+ tree. So the basic idea is that we want to have a balanced tree, and we want it to be not binary, but roughly k-ary, because the cost of randomly accessing a block on disk is significant compared to the size of the block, so a binary structure would be very inefficient. It's much more efficient to put a bunch of keys into each node and have a higher branching factor, and that way be able to have a flatter tree that requires fewer accesses to get from the top to the bottom. Now, the problem then is, how do you balance it? And the mechanism used is actually somewhat like a 2-3 tree. Essentially, although what it does is it actually proceeds from the bottom. So we have a series of, in the simplest case for the B tree, we have a series of records where the top record can have between 0 to k-1 entries, and then each of the lower levels can have between k/2 to k-1 entries in it. For now, we'll assume a tree structure where the actual data is embedded with the well, anyway, so it's it starts out very simply. We've got the root, we add an entry, we add another entry, and so on. We keep these entries in sorted order, which is simple because we're going to have to read it and we're going to have to write it back. It's going to take an insignificant amount of time to sort these keys in memory before writing it back, if this is, for instance, a 4K page. Now, eventually, this block fills up. Oh, I should have. Let me start it like this. Down here. Eventually, it fills up, and so what we do is we, in fact,